work, energy, and electromotive force. Pumping charges, electromotive force. A device that by doing works on the charge carriers maintains a potential difference between a pair of terminals. We call such a device an electromotive force device, and the device is said to provide an electromotive force, which means that it does work on charge carriers. A seat of electromotive force: battery, electric generator, solar cells, thermocouples, electric ears, human being. They all perform the same basic function. They do work on charge carriers and thus maintain a potential difference between their terminals. An electromotive device is sometimes called a seat of electromotive force. The term electromotive force comes from the outdated phrase electromotive force, which was adapted before scientists clearly understood the function of an electromotive force device.
Most batteries consist of two different materials in contact with an electrolyte. We'll use this pair of windmill arms, each containing 4 different metals, to show how the voltage of a simple battery changes with different pairs of metals. A trough of dilute sulfuric acid beneath the windmills provides the electrolyte. We'll dip different pairs of metals into the acid and observe the voltage developed in each case on this voltmeter. Here is copper and copper. Here is copper and iron. Here is copper and zinc. Here is copper and lead.
This pair of different metals has been twisted together to form a simple thermocouple. If we hook the thermocouple to an ammeter and place the tip near a flame, current flows through the ammeter. The closer the thermocouple gets to the flame, the more current flows.
Work, energy, electromotive force. This is a circle. We can present the electromotive force of the device with an arrow that points from the negative terminal towards the positive terminal, as in the figure. The device also produces a current around the circuits in the same direction, clockwise in the figure. A small circle on the electromotive force arrow distinguishes it from the arrows that indicate the current direction. Within the electromotive force device, positive charge carriers move from a region of low electric potential, and thus low electric potential energy, at the negative terminals to a region of higher electric potential and a high electric potential energy at the positive terminal. This motion is just the opposite of what the electric field between the terminals, which points from the positive terminal towards the negative terminal, what causes the charge carriers to do. So there must be some sources of energy within the device, enabling it to do work on the charges and thus forcing them to move as they do. Chemical energy, mechanical energy, biological energy, thermal energy can transfer to electromotive force. or of course it's solar energy. Let us now analyze the circuit of the figure from the point of view of works and the energy transfers in any time interval dt. A charge dq passes through any cross section of the circuit, okay, such as AA prime. This same amount of charge must enter the electromotive force devices at its low potential end and leave at its high potential end. The device must do an amount of work dW on the charge dq to force it to move in this way, from low potential to high potential. We define the electromotive force of the electromotive force device in terms of this work. This is the work you done. This is charge it moves. So electromotive force of these devices equal to dW over dq. In words, the electromotive force of the electromotive force device is the works per unit charge that the device does in moving charge from its low potential terminals to its high potential terminals. The metric system unit for the electromotive force is the joule per coulomb. We define that unit as a volt. 1 volt is 1 joule of 1 coulomb. An ideal electromotive force device is one that lacks any internal resistance to the internal movement of charges from terminal to terminal. The potential difference between the terminals of an ideal electromotive force device is equal to the electromotive force of the device. A real electromotive force device, such as any real battery, has internal resistance to the internal movement of charge. When a real electromotive force device is not connected to a circuit and thus does not have current through it, the potential difference between its terminals is equal to its electromotive force. But when that device has a current through it, the potential difference between the terminals differs from its electromotive force. We will discuss such real battery later. Look at this, okay? This is a battery. This is a battery connected in opposite direction. This is positive, negative. This is positive, negative, okay? Which have what happening, okay? The chemical energy lost, this battery, okay, can work done by motor, make the motor a mass M, and can be thermal energy produced by resistance and can transfer to a chemical energy stored in battery A.